Hello, and welcome to this overview of our simulation modeling work for the Super Intensive Megastore with Integrated Operations, or SIMIO. In this video, we'll be reviewing the background and goals for this project, our modeling approach and assumptions, an analysis of our results, and recommendations for future state facility improvements based on our learnings. Let's kick it off. The models we'll be examining today attempt to create a digital mirror of the activity in an imaginary grocery store distribution center. This center is active 16 hours a day and includes three main areas of interest: dock doors, where trucks arrive throughout the day with deliveries; staging areas, where up to 30 pallet stacks per zone are unloaded and sorted for put away; and storage aisles, where pallets are placed for temporary storage until they're selected for shipping. This model's scope is primarily limited to the receiving and put away process, which ends when pallets are placed on the storage racks. When a truck arrives to the facility, receiving operators, modeled as yellow fork trucks in this system, unload pallets from the truck to a staging area. Eventually, pallets are picked up by either a put-away operator, which are modeled as green fork trucks, or a robotic pallet jack, or RPJ. RPJs need help from a receiving operator in order to scan and load their pallets before dispatching. Put-away operators take the pallets to predetermined rack locations, while the RPJs take them to specified drop-off zones. Replenishment operators, which are modeled as purple fork trucks, take those pallets the rest of the way from the drop-off zones to their final locations. Finally, the red fork truck represents a shipping operator and exists only to form a closed-loop system for the pallets, not to model anything accurate about the shipping process since this is not the focus for this model. A system of complex rules determines which operators handle which pallets and where they go in the facility. The primary goal of our analysis is to determine ways to minimize labor costs for this process, which can be accomplished by the following objectives. 1. Increasing the RPJ's pallet load. In the current state, the system's two RPJs only carry about 25% of the total activity in the system. We would like to increase this to get a better return on investment for the RPJs, which were very capital intensive for both the vehicles themselves and the paths installed to allow them to operate. And 2, decreasing travel time for replenishment operators to bring pallets from drop zones, where they're left by RPJs, to their final destinations. We would also like the system to be robust to variation in inbound traffic. The system should be able to comfortably handle a 20% increase in deliveries without overutilization. And we would like it to be intuitive to human operators. We'd like our improvements to be easy to understand and adapt to, and we'd also like to incorporate lean principles such as standard work. Since lots of information was given about this facility's operations, we had to make many judgments about the level of detail to include in the model. Our modeling approach was highly iterative, starting with defining the functionality of basic features and slowly adding more complex logic. We started with the CAD model of the facility layout and analyzed the historical data to determine the frequency of activity throughout the distribution center. Our first observation was that the dock doors are sectioned into 4 groups, and based on the lack of truck arrivals for Group 2, we're assuming it's dedicated solely to shipping activity. Because the model is focused on put-away, we're ignoring this group. Groups 1 and 4 have many and consistent truck arrivals, while Group 3 is used more sporadically, indicating that it may have mixed inbound and outbound use. We analyzed the historical data to determine the average pallet arrivals per time segment for each hour-long chunk of the week. This was transferred to a rate table in SIMIO. Each source, which generates pallets that are picked up and delivered by trucks to the facility, multiplies the number of pallets for each time segment from the rate table by a scaling factor based on the all-time relative frequency of deliveries at its corresponding dock door. We use the historical data to determine the final destination for each pallet. In our model, we have simplified the location options for pallets to collections of racks instead of individual racks. Using the historical data, we determined the percentage of total putaways for each rack collection. This was populated in a SIMIO table. When each pallet is created, it's assigned a state variable with its final destination based on the probabilities in the location table. Then, when an operator or RPJ picks up the pallet, an add-on process is triggered to determine its destination from the pallet state variable. Several simplifying assumptions were made to create our models. Major ones are as follows. 1. The model description specifies that receivers sort incoming pallets by SKU. Instead of modeling this explicitly, we added a buffer of processing time to the receivers to account for this activity. 2. In the current state, RPJs drop pallets at the closest drop-off location, not the one closest to the final destination. We've elected to simplify this logic and have RPJs drop off pallets close to their final destination, taking care to note the effects on replenish operator travel time and RPJ utilization in our results. 3, we've added an estimated time for receiving operators to help RPJs pre-dispatch to account for the time getting off and back on their fork trucks and scanning pallets. 4, we're assuming that the tracks for the RPJs are magnetic and not physical. This is important because it frees up the RPJs to move in places without tracks as long as they're being manually controlled by human receivers. We elected to use averages from historical data to determine pallet height rather than modeling it dynamically. When trucks arrive, receivers will unload whichever truck they're closest to instead of operating LIFO as specified. Finally, as previously stated, the shipping process was dramatically simplified. Because historical data was directly used to construct the model, our verification and validation steps were hand in hand for this project. We checked the following model aspects in final model results against the historical data. All were either exactly the same or within 10% of expected. The facility operates on the specified work schedule. We checked the number of type of each vehicle running at any given time, the frequency of arrivals at each dock, the frequency of put away at each rack location, the number of pallets in the receiving area at the start of every day, the number of pallets moved by RPJs, the percentage of overall put away activity by RPJs, and the utilization of our replenish operators. Results from a 30-day run of our current state model reflect the issues outlined in the project description. The RPJs are not utilized as efficiently as they could be due to long travel times, and the utilization of human operators is unbalanced. More than half of the travel time for each operator is spent empty, not carrying pallets, just heading to their next destination. Our recommendations for the future state system are broken into 3 categories: improvements for receiving, RPJs, and put-away operators. For receiving: 1. Instead of unloading trucks LIFO as specified, unload FIFO. The company is paying for truck time, and the trucks are probably carrying perishable items, so it makes more sense to get them in and out as quickly as possible. 2. When trucks are unloaded, don't rearrange pallets by SKU. This is overprocessing and placing additional stress on the already highly used receivers. Also, because of the nature of the facility, SKUs coming off a single truck are probably similar. The sorting process already happens with the RPJs and put-away operators. There's no need to double sort. 3. From the historical data, the probability of a pallet ending up in a specific aisle isn't influenced by which dock door it initially arrived at. This is an opportunity for optimization if we're able to better direct the incoming trucks to specific dock doors close to the final destination racks for SKUs they're delivering. For A items, the SKUs should be able to be routed to their final destination much more directly with this method. Some more flexible rack space could be dedicated for B and C items to increase the efficiency of space usage. For the RPJs, we recommend that RPJs take pallets closer to their final destination rather than leaving them at the closest drop-off location. The entire benefit of RPJs is to minimize human travel time, so we should use them to get as close to the pallet's final destinations as possible. This will help decrease replenish operator travel time. RPJs should be allowed to pick up from all dock locations rather than just the Group 4 docks, but they should have dedicated zones to decrease time traveling up and down the horizontal aisles. This is a quick win without adding significant cost because replenish operators can drive the RPJs to the locations that don't currently have magnetic track. We recommend adding one more upward aisle in addition to aisle 77 so the RPJs don't need to travel all the way up and down the facility. Each RPJ should be grouped with a dedicated receiver that manages its pallet loading activity. This is again to decrease the movement up and down the facility and standardize the work for receiving operators. For our put-away operators, define zones for the put-away operators. One put-away operator can handle Group 1 and one can handle Groups 3 and 4. They can rotate once a shift to distribute work evenly. Put-away operators should be able to pick up multiple pallets at a time as long as they're under the height requirement dictated for safety. All of the recommendations outlined previously were implemented in a future state model. When compared to the current state, the number of pallets per hour increases, utilization is more balanced among operators, travel time and distance is decreased for all operators, and overall cost to operate the system for the 30-day run period is decreased. Future work should focus on further verification and validation of the future state system by testing boundary conditions and performing sensitivity analysis. Additional alternatives may also be considered in order to keep moving the facility in a more automated and efficient direction. Thanks to SIMIO for the opportunity to participate in this competition and to our faculty advisor for guidance throughout this project.